Swayam Prabha. Digital India. Educated India.
Now, in this lecture, we will discuss methods of momentum for bodies, and also then we will also discuss one problem of robotic manipulator, where to develop the equations dynamics finds an important role. Now, we have already discussed the concept of momentum for a particle. Now, linear momentum of a particle is mass times the velocity of the particle. It is the product of the mass and velocity. It is a function of mass and velocity, and just simple product. Now, linear momentum of a mass system is the vector sum of the linear momentum of all its particles, because momentum is a vector, kinetic energy is scalar. So, we find out the kinetic energy of this thing, that by summing this one kinetic energies of all the particles. Here also we will do simple summation only. However, that linear momentum is a vector, therefore it has to be summed in that way. If we denote the linear momentum by g and mass and velocity of the ith particle by mi and vi respectively, then g is equal to sigma mi vi. We get that this one for a system of particle, and this is equal to sigma mi ri dot, where ri is the position vector of the particle. Now, when the mass of each particle remains constant, this expression may be written as like this. If we find this is basically g d sigma mi ri divided by dt, d by dt mi. So, mi can come outside and it becomes the same previous expression. Now, if rg is the position vector of mass center and m is the total mass, then m times rg is equal to sigma mi times ri. Thus, we have d mrg by dt is equal to m r dot g is equal to m vg, where vg is the velocity of the mass center of the particles. Now, the particles, they may be finite number of particles or infinite number of particles making the body, or it can be a system of mass. So, we got that equation that momentum of a system of particles is basically nothing but the mass time the velocity of the mass center. This thing is true for rigid as well as non-rigid body. Here we have not made any assumption that about that the particles cannot come towards each other or this thing. So, therefore, this equation is valid for rigid as well as non-rigid body. Now, if we differentiate this expression with respect to the time, then we get g dot is equal to m v dot g is equal to m a, where acceleration of a is the acceleration of the mass center, and this is this will become sigma f, and that will become F net. So sigma F is equal to G dot. We get one relation that sigma F is equal to G dot. Now if we integrate the above relation between T1 and T2, then T1 to T2 F net dt is equal to G2 minus G1. This is the impulse of the total. Now note that all external forces exert impulses whether they do work or not. So all the forces have to be considered in this case, then you can find out G2 minus G1. So this equation can also be used. Now this is about linear momentum. Now we discuss about the angular momentum. Angular momentum is defined as the moment of linear momentum. For a system of particles, the angular momentum Hg about the mass center is given by Hg is equal to sigma rho I cross mi vi, where rho I is the position vector of the particle about the center of mass and vi may be the absolute velocity of this. Say for example, this is the situation. You have a body, this is the axis system, G is the mass center, it is rotating with angular velocity omega, and this is rho I is the distance of the mass from this, and this is Ri and this is Rg. So we have the absolute velocity term is here mi vi, but rho I is the position vector of the particle about the center of the mass. Then you have vi, that means velocity of the particle is r dot I is equal to rho dot I plus r dot g. Hence Hg is equal to sigma rho I cross mi rho dot I plus Rg, and this will become sigma mi rho I cross r dot g plus sigma mi rho I cross rho dot I. This is, as in this case G is the mass center, so the first term in this expression is 0, because mi rho I, if you will do the summation, that will be mass, total mass times the distance of center of mass from the that point, so it is 0. So this portion goes to 0. Therefore Hg is equal to sigma mi rho I cross rho dot I. Now for a rigid body, rho dot I is equal to omega cross rho I. Rho I is the distance of the particle from the mass center, and if we differentiate it, magnitude remains same, only rotation is there. So therefore you get omega cross rho I. Now for a body in plane motion, this simply becomes Hg is equal to rho I square mi omega k. That means this is basically I omega into k. I is the mass moment of inertia of the whole thing, because Hg is equal to sigma mi rho I. So in plane motion it is having only angular velocity omega k, so you will get I omega in that k direction, and this is what that has come. Now Ig is equal to basically sigma mi rho I square, that I can write it Ig, this is Ig. So therefore Hg is equal to Ig omega, that expression we get that in this one, and sigma mg is equal to h dot g we already have. Hence if we take T1 to T2 mg dt is equal to hgi minus hgi. That means now now this is the thing, that if we can find out the impulse of the moments, then that is change into the angular momentum. Now we discussed angular momentum about the center of mass. Now let us discuss angular momentum about any general point O, that is HO is equal to sigma Ri cross mi vi, that is sigma Rg plus rho I cross mi vi. Now this can be written as sigma Rg plus rho I class Mi rho dot I plus R dot G, and that becomes sigma Rg class Mi rho dot I plus R dot G plus sigma rho I class Mi rho dot I plus R dot G, and this is equal to sigma Rg class Mi rho dot I plus sigma Rg class Mi R dot G plus sigma rho I class Mi rho dot I plus sigma rho I class Mi R dot G. Now as G is the mass center, the first and last term in this above expression will be 0. Rg class, Rg is a constant, class Mi rho dot I is 0 because it is about the mass center. You are taking the rate of this one, moment of mass. You take the moment of mass and then differentiate it. So this term becomes 0. And last term also is this one, sigma rho I class Mi, and Mi rho I sigma, this term will become 0. In this case, Mi rho I is equal to 0. So therefore this term also vanishes. Hence you have got HO is equal to sigma Rg class Mi R dot G plus sigma rho I class Mi rho dot I, and this will be equal to M Vg dk. We can write how this comes. Rg R dot G is Vg, and this is the cross product of Rg into Vg. So therefore if the perpendicular distance is d, so therefore mvg into d k and plus I omega into k, rho I class mi this one. So this is I omega into k. D is the length of the perpendicular drawn from 0 to a line passing through G in the direction of Vg. So this is what that you get. H naught is equal to mvg in a plane, that is the this one, and I omega into k, that is for a plane motion. So therefore we can write HO is equal to Ig omega plus mvg into d, and when a body rotates about a fixed point O on the body or body extended, the relation Vg is equal to Rg omega and d is equal to Rg may be substituted into the expression for H0, giving H0 is equal to Ig omega plus mrg square into omega, but Ig plus mrg square is equal to I0. Therefore H0 is equal to I0 omega. So we get H0 is equal to I0 omega. And we also have sigma m0 is equal to I0 omega dot. So therefore T1 to T2 sigma m0 dt is equal to I0 omega 2 minus omega 1. Now we discuss about interconnected rigid bodies. Now this is suppose two bodies are interconnected, and then the moment, linear momentum of one body can be written as G1 is equal to m1 v1 and another body G2 is equal to m2 v2. These may be the two links, and so if two bodies are interconnected, their combined free body diagram can be made. One can make, if sigma f is the net external force on the bodies, then sigma f is equal to G1 dot plus G2 dot is equal to G dot system. So this is the thing. If sigma m0 is the net moment on the bodies about point O, then sigma m0 mo is equal to h dot O1 plus h dot O2 is equal to h dot O system. So about the whole system. And similarly, T1 to T2 f dt is equal to delta G system. And similarly, we can have T1 to T2 m dt is equal to delta H system. So combined power system we can write. Now conservation of momentum applies here also. If the net external force sigma f is 0, this means that delta G is equal to 0, that combined linear momentum remains of the bodies or links connected together remains conserved, although their individual moments may change, momentums may change. So combined linear momentum is this one. Thus, if the net external force on the body is 0, its linear momentum remains conserved. Similarly, if resultant moment about a point is 0, the angular momentum about O remains conserved. That if the resultant moment of the forces about a point is 0, then the angular momentum about O remains conserved. In this case, the angular momentum about G remains constant. So that is what that you get. Now we give that some examples. Let us take that one example of these principles. Now one example is from turbine. This is a turbine bucket. Suppose it is in the beginning, it is stationary, and you have a jet of water impinging with velocity v0, and it gets deflected. The velocity remains unchanged, but it gets deflected at theta, and here also it gets deflected to theta, that type of thing. So then in that case, this will be like this. Now this is so in a turbine, a jet of water is made to impinge on the vanes of turbine and get deflected by a certain angle. During this process, a force is exerted by the jet on the vane, and that causes a rotation of the turbine. The force exerted by the jet on the vane can be determined by applying momentum equations. Now this can be done like this. Rho QA is the rate of mass coming on that. Q is the discharge, A is the area, and rho is this one. So this is rho Q. This is, if you say, or basically QA. Q is the rho Q is the total. If Q is this one, so QA, we can say Q, or it should be that rho times VA. Then applying this one momentum equation, in fact this is rho Q. Applying momentum equation, we have rho Q, and this is minus V0 and plus V cos theta, that is the change in the momentum. So V cos theta minus V0, that is Fx. So water exerts equal and opposite force on the blade. There is no net vertical force in this problem because of symmetry. Now example 2 of interconnected bodies. Suppose two bodies are acting here, that this is M1 and this is M2, and they are put on the inclined plane. This is alpha and this is beta angle inclined with this. Now if blocks of mass M1 and M2 have been kept on the smooth inclined plane, so there are no forces acting, external forces. If they are at rest initially, find out the speed of the blocks after time t. Let t be the tension in the string and v the final speed. So applying impulse momentum equation to m2, that we have m2 sin beta, m2g sin beta minus t into t is equal to m2v. We have to consider this tension T also. Similarly, apply the impulse momentum equation to m1, T minus m1g sin alpha T is equal to m1v. Then what we can do, that we can add these two equations. So we get m2 sin beta minus m1 sin beta is equal to m2 plus m1 divide into v, or we get v is equal to m2 sin beta minus m1 sin alpha divided by m1 plus m2. So this is how we have find out that the velocity of this one particles of masses m1 and m2 by applying the impulse momentum theorem. So by impulse momentum equation has provided us this. Now we will discuss. So we have discussed about the kinetics of bodies, and mostly we have given the examples from the plane motion of the bodies. But now in most of the things we have taken the simple examples so that you can easily solve them with hand calculations and maybe with the help of calculator. But actually the application of dynamics is very broad, and you may have to do number of problems. In that even hand calculations will not be sufficient. One may have to use computer for solving the equations, and there are this thing. But by now you must know how to develop the equations for dynamic this one. So I have taken one example, that dynamic analysis of a two-link rigid robotic manipulator. There are two links which are moving on a plane. This, so it contains number of that very big equations. I am not going to discuss about the solution, but we will form the equations of this thing. What is a robotic manipulator? Robot consists of mostly the links. Suppose this simple link may be there. Now this may be some link. It rotates. When you give a command, it rotates. Now this is one link of a robot. In general, a robotic manipulator can consist of number of links. So it may have, like we can have kinematic chain, that is called, if you have number of links, like 4-bar mechanism. Here this link is fixed, another link connected by pin joint, another like this, and then this is like this. So this is a 1, 2, 3, 4. So this is a 4-bar mechanism, and you see that this chain is closed. This is a chain of links, link 1, 2, 3, 4. They are, link 1 starts at one point and link 4 closes at that point. So this is called closed kinematic chain, and its degree of freedom is 1. That means if we give that one some rotation to 2, then we can know that how much that 4 will move. And we can have open kinematic chain also. The 4, suppose one link was fixed, but I could have connected to 2, and this becomes 3, and this becomes 4. So this is 2, 3, 4. In that case it is a open kinematic, but in robots these type of things are quite often used. This is link number 2, this is 3, this is 4, and they will have independent motion. I can put a motor here, I can put a motor here, I can put a motor at the link number 3. So this is what it can be done, and we can have so this has got 3 degrees of freedom because 3 independent motions are possible. So this is open kinematic chain. So robotic manipulator is an open or closed kinematic chain of rigid rings. Generally we consider that rings to be rigid, otherwise flexibility can also be considered, interconnected by joints and controlled by a programmable device such as computer or microprocessor. This is just linkage, but if we in robotic manipulator, this will be generally controlled by programmable device such as any computer or microprocessor. Then we can, so we take example of just 2 link robotic manipulator, only 2 links are there. This is open kinematic chain, it has got 2 degrees of freedom. Even that, you see that even this will give us complicated equations. Okay, one link is of course simple case. So here that link 1 is of length L1 and this angle is theta 1, and it is pivoted about point O, it can rotate, one motor is put, and link 2 is about this one. So this is theta 2 and this is about this one x1 and this is y2 and this is L2. So this becomes like this one x1 y1 theta 2 L1 L2, this is the thing. So then the length of the 2 links is L1 and L2. Let us consider that the 2 motors fitted at position O and A respectively drive the links. O and A, they are driving the links. Now in this lecture we shall carry out the dynamic analysis of the links. It is assumed that the motion is taking in the horizontal plane. So then we will not have to consider weight. So it is just taking, motion is taking place in the horizontal plane. That means there is a motor fitted at O and there is a motor on A also, that which is driving this thing. So that way it can be done. Now we can make the free body diagram of link 2. Now link 2, this is the link 2. Here I have shown the axis system also. One fixed axis is like this, x and y here. Then you have x1 y1, that is x1 is along the link 1 and y1 is perpendicular to that one. So it is movable coordinate system that is attached at point 1, and similarly x2 y2 is like this, that along this, and this is this thing. Now make the free body diagram of link 2. This link is subjected to torque which is supplied by the joint motor at A. So this is supplied by the joint motor at A. The joint reactions act on the link. So this is they are acting something, we have shown that some fx and fy component, but you know that fx2 and fy2, but we are not going to determine this. It is not necessary to determine the joint reactions, but I have shown here. Also the joint reactions act on the link, so therefore joint reactions are also there and they have been shown just like this. Here now tangential acceleration of any particle P with respect to A is this one, x theta 1 dot dot plus theta 2 dot dot j2, where j2 is the unit vector along x2, and acceleration of A is basically given, that is AA, that is L1 theta 1 dot dot j1, that is centripetal, that is this one tangential acceleration minus L1 theta 1 dot whole square I1, that is centripetal acceleration, where the unit vectors I1 and j1 are in the direction of x1 and y1 respectively. Now resolved component of this acceleration along the normal to the axis of the second link are like this. You resolve these components L1 theta 1 dot dot cos theta 2 plus L1 theta 1 theta 2 into J2. You get like this. So you have obtained the resolved component along this one normal to the axis, because that will be, therefore now absolute tangential acceleration of particle becomes x theta 1 dot dot plus theta 2 2 dot plus L1 theta 1 1 dot dot cos theta 2 plus L1 theta 1 dot square sin theta 2. We have to do this because Newton's law can be applied in non-inertial inertial frame of reference, and therefore we have to talk about the absolute acceleration. Now force on this particle along y2 direction is this, and one single particle m2x theta 1 dot dot plus theta 2 dot dot plus L1 theta 1 dot dot cos theta 2 plus L1 theta 1 dot square sin theta 2 into dx, because the mass of is a small element at distance x is m2 into dx. So m2 dx is the small mass, m2 is the mass per unit length, or it can be a function of per unit length of course, but it can still be a function of x. And the moment of this force about A is basically you multiply it by x perpendicular distance, so it becomes m2 x square theta 1 dot dot plus theta 2 dot dot plus this will be L1 x times, this is x times L1 theta 1 dot dot cos theta 2 dot plus x times L1 theta 1 dot square sin theta 2 into dx. Thus the total torque T2 acting on A through second joint motor is given by T2 is equal to m2 x square theta 1 dot dot plus theta 2 square plus x L1 theta 1 dot dot cos theta 2 plus x L1 theta 1 dot square sin theta 2 dx. This we have to integrate from 0 to L2. So if we integrate this from 0 to L2, we get by integrating m2 L2 square L2 cube by 3 plus theta 1 dot dot plus theta 2 dot dot plus m2 L1 L2 square theta 1 double dot by 2 cos theta 2, and third term is m2 L1 L2 square by 2 theta 1 dot whole square sin theta 2. So this is the expression for that torque coming on ring 2, and you see that this contains not only this term m2 L2 square by this one, but also it will depend on this one, that there are other terms, that acceleration of this and all these type of things. So you are getting these things, and now we find out, but here you are getting only the mass of ring 2, you are not getting the mass of ring 1. Now let us try to find out T1, that means torque for ring 1. For this purpose, consider the free body diagram of two rings together. We are considering that now the free body diagram of the rings together, we could have drawn the free body diagram of only the ring 1. In that case, the joint reactions will be coming at joint A. Those are unknown to us, so we don't want to find out. So therefore, this is the thing, that's why we are doing like this. And you have got in this case that you are showing that joint reactions fx1 fx2 here, and this is the thing. So then and torque T1 is acting. Now what happens that when we consider it together, then we have to consider not only the accelerations of link 1, but you have to consider the accelerations of link 2 also. So for the particles on the first link, tangential acceleration is x times theta 1 dot dot, and that is df is equal to m1 x theta 1 dot dot dx, where m1 is the mass per unit length of link 1. The moment of this mass element about O is m1 x square theta 1 dot dot dx. Thus, the torque contributed by the particles of link 1 is basically T11 particles is 0 to L1 m1 x square theta 1 dot dot dx. If you integrate between 0 to L1, you will get integration gives, and after you put the limits, so 1 by 3 m1 L1 cube theta 1 dot dot. If the total mass of link 1 is m1, then T11 is equal to m1 L1 square by 3, and this becomes theta 1 dot dot. So this is a very nice expression. That means this is basically theta 1 dot dot is equal to alpha. So that means T is equal to I alpha. Had only the first link been present, other link was not there, then matter was finished, because this is the torque contributed by the particles of first link, motor will supply that torque. However, there will be requirement of torque for causing the motion of link 2 also. That also has to be considered, and that portion is little complicated to find out, but we will just discuss about that also. Now about the point O, here the coordinate of point on link 2 is suppose P. So position vector OP is L1 I1 plus x cos theta 2 I1 plus x sin theta 2 J1, and where basically x is equal to AP. This is x. In this figure, this is x. Now if we want to find out that is the position vector of point P, that means position of point P with respect to O. So if we differentiate this position vector twice, we will get the absolute acceleration of point P. That's what we need. Now we differentiate it 2 times, and in differentiation we have to understand that if we differentiate even this one, that say I1 with respect to time, so because it is rotating, therefore that it has to be written that theta 1 dot j like that. So we have to follow the rules of differentiation. We know I dot was that I, if you differentiate unit vector I dot like this, so I, so that is omega into j, and j dot is equal to minus omega I. These type of things we have to this one remember, and then this will be differentiation will give this expression AP is equal to L1 theta 1 dot dot J1 minus L1 theta 1 dot square I1 minus x theta 1 dot dot plus theta 2 dot dot sin theta 2 I1 plus x theta 1 dot dot plus theta 2 dot dot cos theta 2 J1 minus x theta 1 dot plus theta 2 dot whole square cos theta 2 I1 minus x theta 1 dot plus theta 2 dot whole square, then sin theta 2 J1. now this is the expression we have got. So we denote the torque at the joint O due to the motion of the particles of ring 2 by T12. Therefore, T12 is equal to R cross F, cross product, and this will be that F will be basically M2 dx and this thing, and we have to multiply it by cross product F. So this is what happens, that you will get these expressions, that M2 dx L1 square theta 1 dot dot plus L1 into theta 1 dot dot theta 2 dot cos theta 2 minus L1 theta 1 dot plus theta 2 sin theta 2 L1 cos theta 2 theta 1 dot plus x square theta 1 dot dot plus theta 2 dot dot cos square theta 2 minus x square theta 1 dot plus theta 2 dot square, then sin theta 2 cos theta 2 plus x L1 theta 1 dot sin theta 2 plus x square theta 1 dot dot theta 2 square sin square theta 2 plus x square theta 1 dot plus theta 2 dot whole square sin theta 2 cos theta 2, and which can be written as 0 to L2, this is M2 L1 square theta 1 dot dot plus L1 cos theta 1 dot dot plus theta 2 dot dot cos theta 2 minus L1 cos L1 x theta 2 dot dot theta 2 dot square sin theta 2 minus 2 L1 theta 1 dot theta 2 dot sin theta 2, this is L1 x cos theta 2 theta 1 dot plus x square theta 1 dot dot plus theta 2 dot dot dx, which can be now, if we do the integration 0 to L2, particles are 0 to L2, so we get this expression M2 L1 square theta 1 dot plus M2 L1 L2 square by 2 theta 1 dot dot plus theta 2 dot dot cos theta 2 minus M2 L1 L2 square by 2 theta 2 dot square sin theta 2 minus 2 M2 L1 L2 square theta 1 dot theta 2 by 2 sin theta 2 plus M2 L1 L2 square by 2 cos theta 2 theta 1 dot dot plus M2 L2 cube by 3 theta 1 dot dot plus theta 2 dot dot plus x square theta 1 dot dot plus theta 2 dot dot cos square theta 2 minus x square theta 1 dot plus theta 2 dot square sin theta 2 cos theta 2 plus x L1 theta 1 dot sin theta 2 plus x square theta 1 dot dot plus theta 2 dot dot sin square theta 2 plus x square theta 1 dot plus theta 2 dot whole square sin theta 2 cos theta 2. So we are getting very big expressions, lengthy expressions. You must check it by calculations. Okay, there may be, because when you do that such big expressions, there are chances of mistake. That's why nowadays most of these integrations are carried out in computer. One can do the numerical integration, or sometimes that the nowadays softwares are there which can do obtain the closed form integrations also, like MATLAB etc. In that you can do. Otherwise numerical integration is preferred, but I have thought of showing at least one example of the developing the dynamics equation. So I have taken this. Now you must verify these things. Now put M2L2 is equal to M2. M2L2 is the total mass M2. Then you have T12, that means torque required at joint O because of the motion of ring 2, that is m2 L1 square theta 1 dot plus m2 L2 square by 3 theta 2 dot dot plus m2 L1 L2 by 2 cos theta 2 dot dot minus m2 L1 L2 by 2 theta 2 dot square sin theta 2 minus m2 L1 L2 theta 1 dot theta 2 dot sin theta 2. Now this, so therefore the total torque of this one required at point O, joint O of this one comes out to be T is equal to T11 plus T12, that is m1 by 3 L1 square theta 1 dot dot plus m2 L1 square theta 1 dot plus m2 L2 square by 3 theta 2 dot dot plus m2 L1 L2 by 2 cos theta 2 dot dot minus m2 L1 L2 by 2 theta 2 dot sin theta 2 minus m2 L1 L2 theta 1 dot theta 2 dot sin theta 2. So we see that the torque required is influenced by both the motors, and we get that equations which contain these square terms also, non-linear terms are there. We have theta 2 dot square and all these things. So we get the expression for total torque. So we observe that torque of second motor does not depend on the mass of ring 1, whereas the torque on the motor at O depends on the masses of both the rings. So therefore these are the expressions for the torques, and these equations can be solved. Now this so now for any given configuration, solving this type of equation, where you may have to use numerical method. One can be direct problem, that in which somebody may give you that theta 1 as a function of time, theta 2 as a function of time, then it is easy. You can just put that, differentiate and get the value of that. In some cases you may have been prescribed the torque and you have to find out the angular displacements. So in that case the inverse procedure has to be done. So these you have to do some sort of integration, because this then becomes a differential equation and which has to be solved. So numerical methods can also be used. So this is the thing that you have to do, and this will be now if in addition to the masses of the rings, see here we have done simplification in integrations, we have been taking m1 etc. outside. If it was not so, m1 was a function of that x, that means like in a tapered rod and this thing, then we have to put inside that, and some cases we can integrate given m as a function of x, in some cases we have to use the numerical methods only. So that has to be done. Now if in addition to the masses of the rings there is a concentrated masses at the end, then what should be done? Then equations can be developed in the similar way. If you have got concentrated mass, then suppose there is a tip mass, for example MP, which is situated at the tip of the second ring, then same type of expressions can be developed, but the mass per unit length of the second ring may be written as m2 is equal to mp plus delta x minus L2, where mp is the tip mass and m2 is the mass per unit length. It has got a unit of, m2 has got the unit of kg per meter, whereas mp has got the unit of kg, but it has been multiplied by delta x minus L2, where delta x minus L2 is the Dirac delta function, which is defined at L2. So Dirac delta function is that at L2 its value approaches infinity and everywhere else it is 0, and if you integrate Dirac delta function, say between limit 0 to some L2 plus, then you will be getting the value as 1 only. So Dirac delta function has got the unit of 1 by meter. Now so its value is infinite at L2, but if we integrate the Dirac delta function over the small length surrounding L2, we will get 1. In the case of non-uniform link, m2 will be a function of x instead of a constant quantity. So therefore in the integral sign we can put, and that poses no problem. Suppose you have that Dirac delta function will have that property. Suppose you get some term like mp, then delta x minus L2 multiplied by, let us say that something like x dot dx. So it will be simply, it will become mp, that value of that function inside that at that L2. That is the thing. That means if you know you have a function fx which is multiplied by delta x minus L2, this is nothing but the value of the function at L2. So therefore that is g. And in the case of non-uniform link, m2 will be a function of x instead of a constant quantity. Thus all the calculations can be repeated by replacing m2 by m2 plus mp delta x minus L2. Now it is interesting to observe that if both the links are rotating with constant angular velocity, then also the torque will be required. Suppose both are moving in a single link, it is not required, but in this case it is required. In that case the torque on the motor at A will be m2 L1 L2 by 2 theta 1 dot dot square, theta 1 dot square sin theta 2. So because of the angular velocity of the second, if the second link is stationary, then of course that torque will not be, say first link is stationary, then the torque will not be required. But if the first link is not stationary, then this will be required, and sin theta 2, and the torque on the motor at A will be minus m2 L1 L2 by 2 theta 2 dot square sin theta 2 minus m2 L1 L2 theta 1 dot theta 2 dot sin theta 2. So we see that although links are moving with constant velocity, still that torque is required because of the second link. Okay, in the we take the torque with non-inertial inertial system. So therefore now if m2 is 0, then there will not be any requirement of the torque. So this in case the first link is stationary and only the second link rotates, the torque on the second link will be m2 L2 square by 3 theta 1 dot dot, that is theta 2 dot dot basically, that is equal to the mass moment of inertia times the angular acceleration as expected. And in this case for keeping the first link stationary, some torque will have to be applied at O also, and its magnitude is m2 L1 L2 by 2 cos theta 2 dot dot minus m1 L1 L2 by 2 sin theta 2. So we see that this way, by applying only the basic principles of the dynamics, we can solve these type of problems. In always in case of lot of expressions have been developed, but if we apply only the Newton's law to particle, and remember the fact that these laws are valid in inertial reference system only, then we can develop the equations for any type of problem. We have been doing in the previous lectures basically this, we have been developing other expressions like for rigid body and this thing, but basically we apply the equations to particle, then we can always get the expressions. So it may be simple rod rotating, or it may be that robotic manipulator. In that case also this type of things can be applied. So this is that was my purpose of showing this example.